Okay, continuing sample problems for Chem 111. We're going to talk now about calculating molar masses and calculations using the mole. So, let's look at this first one. Ammonium sulfate is a fertilizer widely used as a source of nitrogen. Calculate the molar mass. So like before, everything when we do these calculations, the first thing we have to do is actually calculate or determine what the actual molecular formula is. So we have ammonium sulfate. Ammonium is NH4 plus. Sulfate, one of the polyatomics we need to know, SO4 2 minus. So bring those together, we get a chemical formula of NH4 2 SO4. So then we have to break that down. Calculating molar mass is just like calculating molecular mass, but now we're using grams per mole instead of grams or AMUs. So the elements that we have in this formula is nitrogen, hydrogen, sulfur, and oxygen. Okay, we have for nitrogens, each ammonia has one nitrogen, but there's two ammonia, so we have a total of 2. Hydrogen, again, 4 for each ammonia, but there's 2 of them, so that's 8. Sulfur, there's 1. Oxygen, there is 4. Again, there's no parentheses here, so there's only the 4 in the individual sulfate formula. Again, from the periodic table, the atomic masses, again, are listed here. Nitrogen, 14.01 grams per mole. Hydrogen, 1.008 grams per mole. Sulfur, 32.07. And oxygen, 16.00. So copy those numbers down here. 14.01 grams per mole. Hydrogen, 1.008 grams per mole. Sulfur, 32.07 grams per mole. And oxygen, 16 grams per mole. Multiply those together. We get 2 times 14 is 28.02 grams per mole. From the nitrogen, 8.064 grams per mole from the hydrogen, 32.07 grams per mole from the sulfur, and 64.00 grams per mole from the oxygen. So our final molecular mass, again, we add all of those together. Those down, we end up with 132.15 grams per mole is our molar mass of ammonium sulfate. Calculate the molar mass of ammonium arsenate, NH4O3. We're going to do the same process again, figure out the atoms present, nitrogen, hydrogen, arsenic, oxygen. The total number now, there's 3 ammonias, so that gives us 3 nitrogens, 12 hydrogens, 1 arsenic, and again 4 oxygens. Again, from the periodic table, nitrogen is 14.01, hydrogen 1.008, now arsenic 74.92, and finally oxygen 16.0. So nitrogen 14.01, hydrogen 1.008, again all these are grams per mole. Arsenic was 74.92, and oxygen 16.00 grams per mole. Multiply those together, we get 42.03 grams per mole of nitrogen, 12.096 grams per mole of hydrogen, 74.92 grams per mole of arsenic, and 64.00 grams per mole of oxygen. Then the final molar mass, add all of those up, we get 193.05 grams per mole. Again, the same process we used for calculating molecular mass, we're just using the different unit now of grams per mole as instead of atomic mass units, or AMU. Same process. Remember that we're just now talking about, instead of single atoms, we're talking about moles of each one of those. So for 1 mole of a molecule, we have 3 moles of nitrogen. Let's do, just like before, we'll do a little bit more complicated one. Calculate the mass of CaBO2.6H2O, or calcium borate hexahydrate. Same process again. Figure out how many molecule or atoms we have of each, times by the molar mass. So we have Ca, B, O, and H. Right? So I'm going to go ahead and calculate here the oxygens present from this part of the molecule as well as from the waters. Right? We could do them separately and add them up if we wanted, but I'm just going to combine them together, because oxygen's oxygen no matter where it is. We're just going to take into account the oxygens in both places. So calciums, we only have 1. Boron, now this borate, we have 2 of them. Oxygen, now we have 2 for each one of those. There's 2 of those, so that's a total of 4. Plus we have 6 from the water. So 4 plus 6 is 10. We have 10 oxygens. And then hydrogens, we only have them from here. There's 6 waters. Each water has 2, so that's 12. Again, in the periodic table, calcium 40.08, boron 10.81, oxygen 16.00, and hydrogen 1.008. Transfer those down. 40.09, 8 grams per mole. Boron 10.81 grams per mole. Oxygen 16.00 grams per mole. And hydrogen 1.008 grams per mole. Combine those, the number times the mass, and we get 40.08 grams per mole. 21.62 from the boron, 160 from the oxygen, and 12.096 from the hydrogen. Again, add all of those up. Now for this hydrate, our molar mass is going to be 233.796 grams per mole. Remember from the lab and from last semester or earlier that we can then get rid of these waters by heating this up, driving those waters off, and we would have to take into that account. But if this is the compound we use to make our solution, this is the mass, the molar mass we have to use. So we have 1 mole of all of this, it has that mass. Another one, magnesium fluoride is used in ceramics in the glass industry. What is the mass of 1.72 moles of magnesium fluoride? Now we're taking this one step further. If we talking about converting from mass to this quantity, this definition of a mole. So first thing we have to do is figure out what is our formula. Magnesium fluoride. Right? This is a metal, this is a non-metal, so this is an ionic compound. Magnesium is Mg, fluorine is F, has a +2 charge. Magnesium has a +2 charge because of where it is on the periodic table. Fluorine is a -1, so this is Fe, or MgF2. So we can calculate its molar mass as being the mass of fluorine, magnesium, and the mass of fluorine. So magnesium 1, 2. So 1 magnesium, 2 fluorines. Magnesium has a mass of 24.31. Fluorine has a mass of 19.00. Multiply that out, and then the molar mass is the sum of those two, or 62.31 grams per mole. The same process we've done before. Right? But now we don't have 1 mole, we have more than a mole, and we want to calculate its mass. So from a mole, we want to go from moles to a mass, typically in grams. So to do this conversion, we have to use the molar mass. Right? So we have 1.72 moles of magnesium fluoride. And every mole, so for every 1 mole of magnesium fluoride, from the molar mass, we have 62.31 grams. Right? So if we have more than that, we have a total mass now of 107.1 grams. Right? Just doing the math. But remember, we have to take into account significant figures. Here we're showing 4. The only answer value that they give us is this, 1.72, which has 3. The molar mass, because these came off the periodic table, we can assume that it's not going to play a role in our significant figures, but even if it did, these have 4, right? This one still has 3, so this solution should only have 3 significant figures, or 107 grams magnesium fluoride. Okay. So let's take that a step further. Let's go instead of, or let's, I guess, do this with a different one. Sodium borate is used in a mixture that dissolves gold from its ores. Calculate the mass in grams of 4.68 moles of sodium borate. Same process, or bromate, excuse me. This bromine with the 8 means this is a polyatomic. It's not one of the ones we memorized, but bromine under the periodic table is directly under the chlorine. You have what chlorate is, ClO3 minus. So bromate, because it's directly below, should have the same formula. So this then should be BrO3 negative. Right? Ionic compound, that's Na plus. So we're looking for the mass of sodium bromate. Right? Calculate its molar mass. Or Na, there's 1 times bromine, again 1, and oxygen 3. From the periodic table again, oxygen is 16, bromine 79.90, and sodium 22.99. And 16.00 grams per mole. So this ends up being 79.90, 22.99, and 48.00 for a molar mass of 150.89 grams per mole. Again, repeat the process we did in the last problem. We're going to take the moles that we have, 4.68 moles of sodium bromate times its molar mass. 1 mole of sodium bromate is 150.89 grams. This is going to equal 706.16 grams per mole. Again, we have the last step is always to look at significant figures. Up here we have 3. So this should have an answer of 3. So that would be 706 grams per mole of sodium bromate. So phosphorus pentachloride, PCl5, is a white solid that is pungent, unpleasant odor and is used as a catalyst for certain organic reactions. Calculate the number of moles in 38.7 grams of PCl5. Right? So now we're going to do essentially the reverse of what we did in the last one, where instead of going from grams to moles, we're going to go from, or moles to grams, we're going to go from grams to moles. This again using the molar mass. So calculate the molar mass of PCl5. 1 phosphorus, 5 chlorines. Periodic table, phosphorus is 30.97, chlorine 35.45. Work that out, we end up with 177.25 grams per mole for the chlorine. Add those together, 208.22 grams per mole. Right, now we have grams here. So 38.7 grams PCl5. We want to get rid of the grams, left with moles. So for every 1 mole of PCl5, that weighs or has a mass of 208.22 grams. So we're left with 0.18561 moles. Again, correct for significant figures. Up here we have 3. So our answer should have 3, 0.186 moles of PCl5. Aluminum oxide, Al2O3, is used as a filler for paints and varnishes, as well as a manufacturer of electrical insulators. Calculate the number of moles at 47.51 grams of aluminum oxide. Again, same process. We're going to figure out the number of the molar mass, then convert from mass to moles. So here we have aluminum, oxygen, 2 aluminums, 3 oxygens. Aluminum has a mass of 26.98, oxygen 16 grams per mole, 16 grams per mole. Do that math. 26.98 times 2 is 53.96 grams per mole. 16 times 3 is 48. So the molar mass of aluminum oxide is 101.96 grams per mole. 47.51 grams of aluminum oxide by the molar mass. Up here, 101.96 grams gives us 1 mole. Do that calculation, we end up with 0.46597 moles. Round to the number of significant figures. Now we have 4 here, more there, so this should be rounded to 4 significant figures, or 0.4660 moles of aluminum oxide. So again, we're combining now this idea of the molar mass with dimensional analysis to get us this new value. Let's take this one step further. Let's calculate the number of oxygen atoms in 29.34 grams of sodium sulfate. So if we look at our plan, we're going to go from mass of sodium sulfate, and we want to end up with atoms of oxygen. So this gives us a relationship of either atoms or number of moles. So we can either figure out that mass, we can go to moles, moles to molecules, molecules to atoms, or so we're going to go from mass to moles to molecules to atoms. Right? That's our planned process. So first let's calculate the molar mass of sodium sulfate, NaSO, to that again off the periodic table is 22.99 grams per mole. Sulfur, we're going to use one of them, and from the periodic table 32.07 grams per mole. Oxygen, there are 4 of them, 16.00 grams per mole. Add those up, it's 45.98, 32.07, 64. We're left with 142.059 grams per mole. Right, so then we're going to follow this plan. So we're going to take the 29.34 grams of sodium sulfate, convert to moles, moles on top, grams on the bottom, 142.05 grams of sodium sulfate. Right, so do that math, we're now left with moles. We don't want moles, we want molecules. So from the definition of a mole, for every 1 mole of Na2SO4, we get Avogadro's number, molecules of Na2SO4. Right? So there's 6.022 times 10 to the 23rd things is equal to 1 mole. And from this molecule, for every 1 Na2SO4, we're going to get 4 oxygens atoms. Right? So now from this, we're left with molecules. We want to go to oxygen atoms using this one. So for every 1 Na2SO4, we get 4 oxygen atoms, which is what we wanted. Multiply everything on top, divide everything on bottom, out pops. We should have 4 significant digits at the end, 4.975 times 10 to the 23rd atoms of oxygen. Okay. So we've just now taken this the molar mass and plus the definition of a mole to carry this one step further. So we're not only talking about the whole molecule of this, we're talking about the mass. Let's do one more. So normal breath takes about a liter of air, assuming that the air has an average molar mass of 28.8 grams and a density of 0.97 grams per liter. How many molecules of air do you take with each breath? So the process we're going to take is we're going to figure out from the volume that we breathe, we need to get 2 molecules of air. So we're going to go from volume to mass, mass to moles, and then moles to molecules. So 1.0 liters of air volume to mass, we use the density. So for every 1 liter of air, it weighs 0.797 grams. Mass to moles, the average, if you go through the molar mass of air, was 28.8 grams. And then moles to molecules, 1 mole of air has 6.022 times 10 to the 23rd molecules. Do the math, multiply on top, divide on the bottom, we get 2.0 times 10 to the 22nd molecules of air. Again, same process, we're just taking it one step further through this definition of a mole.